Spectacular images, glowing comas stretched across the sky, dust tails curving millions of kilometers through space, ion tails streaming directly away from the sunday. When we think of comets, we think of what we can see, what telescopes capture, what astrophotographers frame in their fields of view. But what if everything we're seeing is just the beginning? What if the most interesting parts of 3I Atlas exist beyond human vision, streaming through space in wavelengths our eyes cannot detect, composed of particles too small or too dark to reflect visible light? Space-based instruments operating in infrared and ultraviolet are revealing something extraordinary. 3I Atlas doesn't have one tail. It has multiple components, visible structures we've been observing and documenting, and invisible streams that escape detection from ground-based telescopes. Dust particles too fine to scatter visible light efficiently. Gas molecules that emit primarily in wavelengths Earth's atmosphere blocks. This invisible tail isn't speculation. It's being measured, mapped, characterized by instruments designed to see what optical telescopes miss. And what those instruments are finding suggests that the comet we've been watching represents only a fraction of the material 3I Atlas is releasing into space. The hidden component could be substantial, possibly comparable in mass to the visible tail, possibly extending farther, possibly carrying chemistry different from what optical spectroscopy reveals. Understanding this invisible tail is critical because it might preserve information about 3I Atlas formation environment that visible components don't show. When dust particles are very small, when gas molecules emit in blocked wavelengths, when materials don't interact strongly with visible light, they become invisible to conventional observation. But they're still there, still carrying momentum, still interacting with solar radiation and solar wind, still telling stories about where this interstellar visitor came from and what it's made of. This is the story of what we cannot see, the invisible tail of 3I Atlas, and why understanding it might be more important than anything visible light has revealed so far. Understanding why parts of 3I Atlas remain invisible requires understanding how cometary observation works and where conventional techniques fail. Visible light observation detects material that either emits light through molecular fluorescence or reflects sunlight toward observers. For cometary tails, this means dust particles large enough to scatter light efficiently and gas molecules that emit in visible wavelengths when energized by solar ultraviolet radiation. Dust visibility depends on particle size. The physics of light scattering, described by Mie theory, shows that particles scatter light most efficiently when their size is comparable to light's wavelength. Visible light has wavelengths around half a micrometer. Dust particles in this size range, roughly half to several micrometers, scatter visible light strongly and appear bright. But cometary activity produces dust across enormous size ranges, from nanometer-scale grains up to millimeter-sized pebbles. The very smallest grains, nanometers to tens of nanometers, scatter visible light poorly. They're simply too small. The interaction is weak. These particles remain nearly invisible to optical telescopes, despite being present in substantial quantities. Similarly, the largest particles, tens of micrometers and larger, have low surface area to mass ratios. They scatter light, but the scattered light per unit mass decreases as size increases. Very large grains and pebbles are inefficient scatterers. Much of the mass in cometary dust tails might exist in these optically dim size ranges. Gas visibility has different constraints. Molecules emit light when energized by solar radiation, but emission occurs at specific wavelengths determined by quantum mechanical structure. Many important cometary molecules emit primarily in ultraviolet or infrared wavelengths that Earth's atmosphere absorbs. Ground-based telescopes cannot detect these emissions because the light never reaches the surface. Water vapor, the dominant molecule in most comets, emits strongly in infrared. From the ground, this emission is blocked by atmospheric water vapor. Hydroxyl radicals, the photodissociation product of water, emit in ultraviolet and visible. The visible lines are detectable, but much of the emission occurs in ultraviolet wavelengths blocked by the atmosphere. Carbon dioxide emits primarily in infrared. Carbon monoxide emits in ultraviolet and infrared. Many organic molecules emit in infrared. Without space-based instruments or specialized ground-based techniques, much of the molecular emission from comets remains unobserved. This is why 3I Atlas invisible tail exists, not because material isn't there, but because much of what's being released doesn't interact with visible light in ways ground-based telescopes can detect. Subscribe now, because understanding what space-based instruments are revealing about this invisible tail might change how we think about cometary composition and activity. Infrared observation reveals what visible light misses. Infrared wavelengths, longer than red light, interact differently with matter. Small dust particles that scatter visible light poorly can emit thermal infrared radiation if they're warm. Gas molecules that don't emit visibly often emit strongly in infrared. Space-based infrared instruments, observing 3I Atlas, detect significant thermal emission from dust that isn't visible optically. This dust is present in the coma and tail, but doesn't contribute substantially to visible brightness. The particles might be very small, below the optimal size for visible light scattering. Or they might be large and dark, absorbing sunlight and re-radiating it as infrared, rather than reflecting it visibly. The infrared signature allows scientists to estimate the total dust mass being released, not just the visible fraction. Preliminary analysis suggests the infrared detected dust might represent a significant fraction of total dust production, possibly comparable to or exceeding the visible dust mass. This means optical observations might be detecting less than half the dust actually present. Infrared spectroscopy also reveals gas that's invisible optically. Water vapor, carbon dioxide, organic molecules all show characteristic infrared emission lines. Space-based infrared spectrometers can measure these emissions, determining molecular abundances that can't be accessed from the ground. For 3I Atlas, infrared observations are particularly valuable given the suspected carbon dioxide-rich composition. If carbon dioxide dominates, much of the gas emission will be in infrared wavelengths. Visible light observations would miss this component entirely, severely underestimating total gas production. Infrared detection provides the complete picture. The infrared tail extends beyond the visible tail. Because thermal emission doesn't depend on scattering sunlight, infrared instruments can detect warm dust even when it's too sparse or too small to be visible. Tracking this extended infrared tail reveals how dust spreads through space over time, how solar heating affects particles at different distances, and how dust properties evolve as material ages. Ultraviolet observation reveals another invisible component. Many molecules emit strongly in ultraviolet wavelengths when energized by solar radiation. But Earth's atmosphere absorbs ultraviolet light below about 300 nanometers. All the shorter ultraviolet emission, where many important molecular transitions occur, is blocked from ground-based observation. Space-based ultraviolet instruments detect emission that never reaches Earth's surface. Hydroxyl radicals emit strongly in the far ultraviolet. Atomic hydrogen, produced when water molecules are completely dissociated, emits in ultraviolet. Carbon, oxygen, nitrogen atoms all have strong ultraviolet emission lines. For 3I Atlas, ultraviolet observations during perihelion captured emission from these species. The hydroxyl emission confirms active water sublimation. Atomic hydrogen emission reveals the rate at which water is being completely broken apart by solar radiation. Carbon emission might indicate carbon dioxide or carbon monoxide dissociation. The ultraviolet tail extends even farther than infrared or visible tails. Atomic hydrogen, being extremely light, is pushed outward by solar radiation pressure very efficiently. Hydrogen atoms from 3I Atlas spread across enormous distances, creating an extended hydrogen cloud that dwarfs the visible coma. This hydrogen cloud is completely invisible to optical observation, but shows clearly in ultraviolet. Mapping the hydrogen cloud reveals water production rates integrated over days to weeks. As water sublimates, dissociates, and the hydrogen spreads, it creates a trail marking where the comet has been. This trail preserves information about activity history that point observations don't capture. Ultraviolet spectroscopy also detects molecules and atoms that might be present in low abundances but emit efficiently in ultraviolet. Species that wouldn't show up in visible spectra might be detectable in ultraviolet if they have strong transitions at those wavelengths. This expands the molecular inventory that can be measured, providing more complete compositional analysis. Comment below. If you could observe 3I Atlas in any wavelength range, which would you choose and why? The invisible tail reveals something crucial about dust properties. By comparing visible light observations with infrared measurements, scientists can infer the dust particle size distribution. Different sized particles contribute differently to visible versus infrared brightness. If most dust existed in the optimal size range for visible light scattering, visible and infrared observations would show similar distribution. But if substantial dust mass exists in very small or very large particles, infrared would detect material that visible light misses. For 3I Atlas, preliminary comparison suggests the dust size distribution might be unusual. Infrared detections indicate more small grain or large grain dust than typical solar system comets produce. This could reflect differences in how the nucleus fractures and releases material, or it could indicate that the dust itself has different properties, perhaps different composition or structure that affects how it breaks apart. Very small dust grains, nanometer scale, can be produced by several mechanisms: shattering of larger grains through collisions, condensation of vapor directly into solid grains in the coma, breakup of fragile aggregates through thermal stress. Each mechanism has different implications for comet structure and composition. If 3I Atlas produces abundant nanometer scale dust, it suggests either that the nucleus material is unusually fragile, breaking into very small pieces easily, or that vapor densities in the coma are high enough for significant grain condensation. Either way, it reveals something about the object's physical properties. Large dust grains and pebbles, if abundant, indicate that the nucleus can release substantial chunks of material, not just fine dust. This might occur if the structure is weak and rubble-like, allowing fragments to separate easily, or if explosive gas release entrains large particles and ejects them. Understanding dust size distribution is critical for interpreting tail dynamics. Radiation pressure acts more strongly on small particles. Solar-wind interactions affect different sizes differently. The visible tail structure depends on particle sizes. If much of the dust mass exists in sizes that contribute minimally to visible structure, the tail we see doesn't represent the bulk of material being released. The existence of substantial invisible components has implications for understanding 3I Atlas composition. If much of the dust is optically dark or wrong size for efficient visible scattering, it might have different composition than the visible dust. In solar system comets, dust composition is predominantly silicate minerals and organic compounds. Silicates are relatively bright at visible wavelengths, but if 3I Atlas formed in a more carbon-rich environment, its dust might contain more carbonaceous material. Carbon-rich dust tends to be darker, absorbing rather than reflecting visible light. This would make it preferentially detectable in infrared emission rather than visible reflection. The suspected carbon dioxide dominance in the gas also suggests carbon-enriched composition generally. If carbon dioxide dominates over water, carbon likely exceeds oxygen in the bulk composition. This carbon excess must go somewhere. Some forms carbon monoxide, some might form organic molecules, and some might be incorporated into dust as carbonaceous material. Dark carbonaceous dust would explain why infrared observations detect significant dust mass that isn't visible optically. The dust exists and is warm enough to emit thermally, but it doesn't reflect sunlight efficiently because it's too dark. This interpretation fits with the overall picture of 3I Atlas as an object formed in a carbon-rich stellar environment. The invisible gas component also constrains composition. If ultraviolet and infrared spectroscopy reveal molecules not detected in visible wavelengths, the complete molecular inventory expands. Species that appeared absent might simply emit in blocked wavelengths. Only by combining visible, infrared, and ultraviolet observations do we obtain the full compositional picture. Detecting and characterizing invisible tail components is technically challenging. It requires space-based instruments, which are expensive, limited in number, and heavily oversubscribed. Observation time on Hubble Space Telescope or James Webb Space Telescope is precious. Allocating time to study comet tails competes with countless other scientific priorities. Ground-based infrared astronomy can access some near-infrared wavelengths where atmospheric absorption is low, but the most informative infrared spectroscopy requires space-based platforms. Similarly, ultraviolet astronomy is almost entirely space-based. Earth's atmosphere blocks most UV. This means that characterizing 3I Atlas invisible tail components requires coordinating observations across multiple spacecraft and ground-based facilities, integrating data sets from instruments with different capabilities and wavelength coverage. Data formats differ. Calibration procedures differ. Combining observations into coherent analysis requires substantial effort. But the effort is justified because the invisible components might represent the majority of material being released. Understanding cometary activity while ignoring what you can't see in visible light is like trying to understand an elephant while only looking at its visible parts and ignoring everything in shadow. You get an incomplete and potentially misleading picture. For 3I Atlas specifically, given its interstellar origin and unusual properties, comprehensive characterization requires all available wavelength coverage. Every wavelength regime reveals different information. Visible light shows readily scattered dust and specific molecular emissions. Infrared reveals thermal emission from all dust and emission from infrared active molecules. Ultraviolet shows highly energetic emissions and light atomic species. Only by combining all these observations can scientists construct complete models of what's actually happening as 3I Atlas releases material into space. As 3I Atlas recedes from the Sun, the invisible tail components will evolve. Dust will cool, changing its infrared emission characteristics. Gas production will decline as solar radiation intensity decreases and sublimation slows. Monitoring these changes reveals how activity responds to changing solar conditions. Infrared observations over coming months will track dust temperature as a function of solar distance. This constrains dust properties like size and composition because different materials cool at different rates. Dark dust cools faster than bright dust. Small particles cool faster than large particles. The temperature evolution fingerprints these properties. Ultraviolet observations will track how quickly the extended hydrogen cloud disperses. As water production declines, hydrogen emission should fade. The rate of fading reveals water production history and how hydrogen atoms spread through space under solar radiation pressure. If 3I Atlas activity includes episodic outbursts, invisible components might show different temporal evolution than visible components. Gas and small dust respond faster to changing conditions than large dust. Infrared and ultraviolet monitoring might detect activity changes that aren't obvious in visible light, providing early warning of structural changes or revealing internal composition variations. Long-term monitoring also allows comparison with solar system comets at similar distances. Do infrared and ultraviolet emissions scale the same way with solar distance? Or do they show different trends suggesting composition differences? Statistical comparison between 3I Atlas and local comets will quantify how unusual this interstellar visitor truly is. As I record this, 3I Atlas continues outbound from perihelion, its visible tail stretching across the sky, captured in thousands of images from professional observatories and amateur telescopes worldwide. But beyond what those images show, beyond what human eyes can see, invisible streams of gas and dust extend farther, carrying information about this interstellar visitor that visible light alone cannot reveal. The infrared tail, composed of dust too small or too dark to scatter, visible light efficiently but warm enough to emit thermal radiation. The ultraviolet tail, glowing with emissions from atoms and molecules energized by solar radiation, but emitting at wavelengths Earth's atmosphere blocks. Both invisible from the ground, both measurable from space, both essential for understanding what 3I Atlas is actually doing. This invisible tail is not a minor detail. It might represent half or more of the material being released. Ignoring it means misunderstanding the comet's activity, composition, and how it responds to solar heating. Including it provides the complete picture of an interstellar visitor whose properties differ fundamentally from solar system comets. Scientists are working to characterize these invisible components through space-based observation and sophisticated analysis, combining infrared, ultraviolet, and visible data sets, modeling dust size distributions, calculating gas production rates from multiple molecular species, building comprehensive understanding piece by piece. The work is challenging but revealing. Each wavelength regime adds information. Each measurement constrains models. Each observation brings us closer to understanding not just what 3I Atlas looks like, but what it actually is, where it came from, how it formed, what materials compose it, what processes drive its activity. 3I Atlas' invisible tail reminds us that appearances can be deceiving. What we see with our eyes or capture with optical telescopes represents only part of reality. The full story requires looking beyond visible light, employing instruments that extend human perception into wavelengths we cannot naturally detect. And in those invisible wavelengths, the comet reveals secrets that visible light hides. Dust properties that constrain formation conditions, gas chemistry that reveals stellar environment, activity patterns that fingerprint internal structure, all waiting to be discovered by those willing to look beyond what eyes can see. Comment below, does it surprise you that we might be seeing less than half of what 3I Atlas is actually releasing? And subscribe, because as infrared and ultraviolet observations continue and analysis progresses, we'll bring you updates on what scientists learn from this invisible tail and what it teaches us about the true nature of interstellar visitors passing through our solar system. The comet with the invisible tail continues its journey. The hidden components stream through space. And somewhere in the infrared glow and ultraviolet emissions, the complete story of this ancient traveler's composition and origin is being written in light we cannot see, but instruments can measure